Today we are going to discuss about the inverse of the linear transformation. And because we know that when we work with finite dimensional cases like Rm and Rn, every linear transformation is uniquely determined by a matrix. So the inverse of a linear transformation is going to be also identified with the inverse of some matrices. So let's consider some diagram that represents some transformation. The first one, you can go from the left to the right easily. When you want to go back from y to x, this is okay, but y3 is not okay anymore. Because for y3, we cannot decide whether it will take y3 to x3 or take y3 to x4. Now for this transformation, it takes x1 to y1, x2 to y2, x3 to y3. So it's okay to go back from y1 back to x1, y2 back to x2, y3 back to x3. But then when we consider y4, it has no place to go to. So we cannot go back from y to x. In linear algebra, we are going to say this t and this t, they are not invertible because you cannot invert the process. For this one, you cannot go back because you cannot decide where to go. For this one, you cannot go back simply because there is nothing to go back. However, this is invertible because you can always go back from y to x. All right. So what's the difference between the three here? For this one, every y has an x, and that x is uniquely determined. Right? This is like the function tx equals y has more than one solution when considering y equals y3. What about this one? It's like the equation tx equals y has no solution when considering y being the specific vector y4. But for this one, this is very nice. The equation tx equals y has exactly one solution for every y you consider. Right? For example, for y1, that's x1 being the solution for this equation, and that's the only solution you can find. For this y2, x2 is the only solution you can find to solve the equation here. y3, x3 is the only solution. y4, x4 is the only solution. So, motivated by these observations here, right, we are going to have the definition of what it means by an invertible linear transformation. So suppose that T is a transformation goes from V to W. This transformation is said to be invertible if the equation Tx equals y always has a unique solution regardless of the choice you made for y. Because being invertible means you can go back from W to V. So the inverse transformation will take the vector in W back to the unit vector in V. And we write it as T to the negative 1. Right, which is natural. Because T goes from V to W, T inverse is going to go back from W to V. W to V. And in order to compute what T inverse is going to take back to, in other words, if you start with a Y in W, and you wonder what is the X vector that is corresponding to T inverse of Y, then it's the same as solving the equation Tx equals Y. So we say T inverse of Y equals X if and only if Tx equals Y. Now, if the transformation is a linear transformation, then its inverse is also linear. Now, we observe that when V is a finite dimensional space, say Rn, W is a finite dimensional space, Rm. If T is invertible, then M and N are the same. Surprising, right? Because being invertible means that for every x on the left, you only have one and only one y from the right, and for every y on the right, you only have one and only one x associated to the y. So that means somehow that the number of vectors on the left and the numbers of vectors on the right are the same. Then it makes sense to make the intuitive guess that the dimensions are the same. Right. This is not very rigorous to say that, but it makes sense. And if the dimensions are the same, the m and the n are the same. All right. And because linear transformation can be represented by matrices, the m and the n are the same means that the matrices that represent the linear transformation T and its inverse are going to be square matrices, meaning the number of rows and the number of columns are the same. Now, let A be the matrix that represents T. At that time, we know that there will be some matrix that represent T inverse. So we are going to denote as A to the negative 1 and call A to the negative 1 the inverse of the matrix A. Now we say that A is invertible if we have A negative 1 here. If this exists, then we have A being invertible, just like we say T is invertible. Tx is the same as A times x, so Tx equals y is A times x equals y. The transformation is invertible if the equation Tx equals y has a unique solution. So translated to the matrix point of view, A is invertible if the equation Ax equals y has a unique solution for any y. But then if you turn back several pages before in the book, this is exactly the same way when we used to define a non-singular matrix. So the word invertible meaning the same as the word non-singular. Now I would like to show you an example of how we compute the T inverse here. So first, let's consider this example. Prove that T given by this formula is invertible. Then find the formula for its inverse and the matrices that represent the inverse and the original matrix. So the transformation T is going from a vector space V to a vector space W. It's going to take a vector in V, say X, and transform it into a vector Y in W that we usually denote as T of X. What is the domain space V in this case? Now, if you look at the formula, T is going to take effect on the column vector that has two entries, so that's exactly R2. It will take in an R2 vector, process the vector, and spit out another column vector that has two entries. So the target space is going to be R2 as well. Instead of writing just X, we can write X1 and X2. Instead of writing Y, we can write Y1 and Y2. And instead of writing T of X, we can write T of X1 and X2. Right? How are you going to compute the Y1 and Y2 here? That's what it means by the formula given to you on the top here. All right. In order to get the Y's, you need to add X1 and X2, and then for the second entry, you subtract them accordingly. So Y1 will be X1 plus X2, and Y2 will be X1 minus X2. In order to prove that T is invertible, we are going to stick with the definition. What do we need to show? So get back to the definition here. A transformation T is invertible if the equation Tx equals y always has a unique solution regardless of the choice of y. So that means we need to start with an arbitrary y, any y, arbitrary, right? You don't need to pick a specific y, just an arbitrary y. You need to prove that the equation Tx equals y always gives you a unique solution for the x vector. But this is the same as solving the following equation. Now, solving this equation is equivalent to solving the following equation. we consider T. Now, this is the matrix A that represents T. And so solving this equation is the same as solving this equation. In order to solve this one, we are going to write the augmented matrix of the system of equations here, right? But we know that the augmented matrix will have the coefficients being exactly the coefficients of the matrix A that we use to multiply with the vector x here. So we write 1, 1, 1, negative 1. And then on the right, we are going to have y1, y2. So take row 2, subtract by row 1. Divide the second row by negative 2 to get the pivot entry being 1, right? Then next, you use this number 1 to zero out the entry above it to make the row reduced echelon form. When we get to this part, we know that regardless of what y values or what y vector you plug in, right? You can always find the x vector, and the x vector is going to be uniquely determined. So this means that you have successfully solved for x1 and x2 or the vector x. And that is going to be equals to 1/2 y1 plus 1/2 y2. The second entry will be 1/2 y1 minus 1/2 y2. So that's the inverse transformation on the y vector. And if you wish to see it clearly as the matrix form, then this is actually 1/2, 1/2, 1/2, negative 1/2, multiplied with the column vector y1 and y2. So this inverse transformation is in fact just the same as multiplying this matrix with the vector y that you wish to find the inverse image. In other words, if you write this one as short as just x, then this is the formula for the T inverse of the vector y. And this matrix, you can write it as B, but because we know that this matrix is closely associated to the invertibility of the transformation associated to the matrix A, so we write it as A inverse. All right, and so T inverse of y equals A inverse times y. And that is going to give you the corresponding x value that you want to find. So we have seen how we are going to find the inverse matrix. Now let me go back to the beginning and I'm going to do something to reduce our work. Instead of writing y2 underneath y1 like this, I'm going to write 1 times y1 plus 0 times y2. And here 0 times y1 plus 1 times y2. And here it's going to be 1 times y1, negative 1 times y1, 1 times y2, and 0 times y2. This is 1 times y1 plus 0 times y2. Now, if you pay attention, we had to write y1 and y2 over again and again, but they actually are not what being changed. The things that are being changed are the coefficients associated to y1 and y2. Right? The coefficients are the ones that are changing, not the y's. Why do we have to write something over again and again without any use? Let's go ahead and erase them. Now you can even erase the plus 1 here and the plus here, because the plus just means positive value number here. Right? And look, if you do so, then your right hand side looks like some matrices, right, that are changing over time. This guy is in fact the matrix A that represents the T. This guy is in fact the identity matrix that is of the same size of A, 2 by 2 identity matrix. Now you do the transformation. At the end, what you get is that the A has been transformed into the identity matrix. And on the right, the I2 has been transformed into the inverse of A. So this is the inverse of the matrix A. All right, so the theory is very simple. If you want to find the inverse matrix of a matrix A, first you write matrix A and then add in to the right of A the identity matrix. That is going to create a bigger matrix with A on the left and the identity matrix on the right, and they are going to be differentiated by the column in between them. Try to use row reduced echelon form to reduce A into the identity matrix if possible. At that time, when you get from A to the identity matrix, the right hand side will bring you from the identity matrix to what being called the inverse of A. And that's the whole theory behind the inverse matrices. And because we know that matrices are associated naturally with the finite dimensional linear transformation, that's also the way we find the inverse of the transformation. To find the inverse of a square matrix, use row operations and try to reduce the matrix of A on the left and the identity matrix of the same size with A on the right. Try to reduce it to the row reduced echelon form. Of course, if you can get to the row reduced echelon form, the left hand side matrix is going to be the identity matrix. If you can bring A to the identity matrix, then the I is going to go to the C. In the example I showed you, we can, but in general, can we always find that? The answer is not always, and that's why I put a question mark. So in order to help you do your homework assignment and find the inverse matrix more effectively, first you row reduce A and I to the echelon form. From the echelon form, it will tell you whether you should go further and obtain the row reduced echelon form or not. So this is in fact just the row reduced echelon form. From the echelon form, if you see that there is a zero row in the echelon form here, then there is no inverse for A, right? Because that is going to be like 0, 0, 0, a bunch of 0, and then something here. That is not 0. So that means you are going to have 0 times x1, 0 times x2, 0 times xn equal to something not 0. That's unsolvable. Even if this is going to give you something exactly like 0, that just means that you are going to have infinitely many solutions. And that violates the definition of being invertible. Being invertible, there should only be one solution. So the existence of non-zero row, if any, just means that A is not invertible. You cannot solve for it and get a unique solution. You may have no solution or infinitely many solutions. Now, if there is no zero row, then proceed further to get the row reduced echelon form. That is going to give you the inverse matrix. All right. Now I'm going to work on this example. Right. Find the inverse of the matrix here. I'm going to call it the matrix A. In order to find the inverse of the matrix A, we are going to make a bigger matrix by putting the identity matrix to the right of this matrix, and then try to get to the row reduced echelon form. But wait a minute. In the middle, check if the echelon form has 0 rows or not. If you see some 0 row, stop right away. You don't need to waste your time to get to this part. Now you are going to transform this into an echelon form. If you do that correctly, you should get the following. All right, you see no 0 rows. Well, that's good because this means that A inverse exists. And because we know the existence is for sure, we proceed further to the row reduced echelon form. We know that we are not going to waste our time for something that does not exist, right? If you do that correctly, your left-hand side matrix should become the identity matrix. At that time, the right-hand side is going to become what is called the inverse. And in this case, the inverse is this matrix. Right, so this is going to be your A inverse. theorem 3.8, the product of two matrices that are inverses of each other will be the identity matrix. Next, theorem 3.9. If a square matrix is invertible, then the rank of the matrix will be the same as the size of the matrix. And this is equivalent, right? If the rank is n, then that matrix is invertible. So let's prove theorem 3.9. A is invertible is the same as the transformation Tx equals Ax is invertible. Saying a matrix is invertible is the same as saying that the transformation associated to the matrix is also invertible. But this is the same as saying that the equation Tx equals y has a unique solution for any y, right? This is the same as Ax equals y has a unique solution for any y. The magic thing is right here that I'm going to just write it and put triple question marks, and I'm going to come back and prove it later. Now, if Ax equals y has a unique solution, then when you apply this for y being 0, of course, this implies right away that Ax equals 0 has a unique solution. How can we go back from the equation Ax equals 0 has a unique solution to prove that Ax equals y also has a unique solution for any y? That's the hard thing that we need to prove. Right, let's accept this, and I'm going to come back and prove it later. Now, this is the homogeneous equation. It may have infinitely many solutions or one solution. But in this case, because we know that it has a unique solution, then x equals 0 is the only solution for this equation. And then this is equivalent with saying that the null space of A has the only solution, that is vector 0. But this is the same as saying that the dimension of the null space of A, which is the nullity of A, is 0. Then by the rank nullity theorem, we are going to have rank of A equals n, the size of A, the number of columns, minus the nullity of A, which is n minus 0. Now I'm going to prove this. All right, as I said, this direction is obvious because we just apply y equals to 0. However, how can we go back? That's surprising, right? We need only to know one equation and we can say something about all other equations. Suppose Ax equals to 0 has a unique solution. We need to show Ax equals y also has a unique solution for any y, right? Well, in order to prove the uniqueness, we have been doing this for quite several times. We start with two things, and we will prove that the two are the same. So let's suppose that x1 and x2 are the solutions for Ax equals y. Being solution means Ax1 being y and Ax2 being y. All right, so if we subtract them, we are going to have Ax1 minus Ax2 being y minus y, which is 0. And by the linearity of matrix multiplication, we have A times this. Exactly, this is by the distributive law of matrix multiplication. Right? And because Ax equals to 0 has a unique solution, and this means that x1 minus x2 is the solution for Ax equals to 0, right? So this implies that x equals x1 minus x2 is a solution for the equation Ax equals to 0. This implies that x1 minus x2 has to be 0 because the only solution is 0, right? And so this implies x1 equals x2. And we have proven the uniqueness, right? Next, we are going to prove theorem 10. Theorem 10 is useful when you want to check if a matrix B is the inverse of a given matrix A. Of course, here A and B are square matrices. B is going to be the inverse matrix. If when we multiply B to A, the result is the identity matrix. And surprisingly, you don't have to check that for A times B and B times A at the same time. You only need to check one of them, either or. If you have this, then A is invertible and B is the inverse matrix. Or you can check this, and if you have this, then it implies A being invertible and B is the inverse matrix. So I'm going to prove this part. AB equals I implies A invertible and B is the inverse matrix for A. Now we know before that if we multiply two matrices together, the rank of the product is less than the minimum of the rank of each of the matrix. But wait, what is A times B in this case? It's the I. So this is the rank of I. What is the size of the I here? Because A and B are n by n matrices, the I, the result is going to be an n by n matrix. And the rank of the I is of course n, because I has n non-zero rows and I is in echelon form already. So this implies that n is less than or equals to the rank of I. And because it is less than the minimum, that means it is less than both of them. So we use rank of A for our purposes here. But then this immediately implies that the rank of A is n because A has n rows. If A has n rows, then the biggest number of non-zero rows in the row reduced echelon form you can get from A is going to be n, right? You cannot go past n rows here. Then what does that mean by having rank of A equals to n? Well, theorem 3.9 gives you a way to check the invertibility of the matrix. You can row reduce it and find the rank. If the number of non-zero rows or the rank is exactly the number of rows in the matrix, then the matrix is invertible. By theorem 3.9, from here, we can conclude that A is invertible. So we have proven the first part. A is invertible means that A inverse exists. And we can compute. Now our next job is to prove that B is in fact the inverse of A. In order to see that, we'll start with the fact that AB equals I, right? This is what we have. So since AB equals the identity matrix, we can apply or multiply A inverse to the left of the matrix on the left and multiply A inverse to the left of the matrix on the right. Pay attention onto the order here because matrix multiplication is not commutative. So if you ever write something like this, the logic is wrong here because matrix multiplication is not commutative in general. By the associativity of the matrix multiplication, we can multiply the first two matrices before we multiply B, right? On the other hand, we multiply A inverse with I, the identity matrix. We of course is going to get the A inverse. Now again, A inverse times A is going to be I. That is by theorem 3.8. Right here. So we have I times B equals A inverse. But then again, when you multiply an identity matrix with any other matrix, it's going to give you the exact matrix that you started with. So B equals A inverse, and we are done. Now I have just proven the first part of the theorem. AB equals I implies B equals A inverse. Your job at home is to mimic my proof and try to write something for BA equals I implies the invertibility for A and B equals A inverse.